Hi everybody, very good evening and a warm welcome to Vedantu Enlite. What's up? How are you all? How are you all? Am I audible and visible? Please let me know in the chat box, everyone. I think I am, right? Can you see me and hear me, guys? Audible and visible, right? Yes, hi Ashwin. Hello everybody. Okay, so very good evening and a warm welcome to Vedantu Enlite, and this is your master teacher Nabamita Bhattacharya, as probably you guys know it, but most of the students, they call me Nabamita Ma'am. So if you want to call me Nabamita Ma'am, sure, go ahead. I have no problem with it. Now that I'm live, please quickly go ahead and call up your friends. Today we are going to start with crystal field theory. In the last session, we read till valence bond theory. Okay, I do see very less students. Guys, can you please call up your friends quickly and also interact on the chat box. Come on. Ashwin, Tilagavati and hi Prab. Hello everybody. Okay. Alright, shall we start or are there more students coming in? I can't understand. More students coming in? No? What's going on? Okay, Ashwin, you are dabbing also. Great. Amazing. Do I have to wait for some time? Hi Shakti. Hello. Very good evening everyone. Hello everybody. Okay. Alright, so how many of you remember what we did in the last session? And I understand that we were supposed to do it actually, we were actually supposed to do it long back, but on Wednesday I fell sick, and yesterday also, there was full hustle bustle of Diwali celebrations and somehow I could not take class. But anyway, here I am, and from tomorrow our Diwali vacation is going to start, our Diwali holidays is going to start. So what I'm going to do is, this will be live, but after that I will start with P block, and the P block classes will be recorded. So I request you all, in fact I suggest you that please do watch those videos, because as soon as I come back, we will do a test on all of these, okay? We will do a test on crystal field theory, valence bond theory, the whole of coordination compounds and the P block as well. So I would require you all to watch this session, okay? Watch this session. Do watch this session. Yes. Hi Prab. Hello Jivashri. Hello Rudranath. Hi Ashwin. Let all join. But then you have to call them. Yes, no one is joining. This is sad. Thank you Ashwin. Thank you so much. Yes, please quickly go call up your friends. I also did post it on Telegram. What happened? Everyone forgot or what? Good evening, Harini. Good evening. Hello. Okay, so now tell me, how many of you do remember the valence bond theory? Yes, I think it was made quite easy for you, right? And everybody got to know it, everybody understood it. So today we are going to understand crystal field theory. Now the question is that why do we need to study two theories? Obviously, because valence bond theory was not able to explain a lot of things, right? Valence bond theory could not explain a lot of things, and that's why crystal field theory comes into the picture. Now, when we are studying about crystal field theory, I'm going to start, okay? Let other students just join in as they keep coming. That's fine. Alright, so in case of crystal field theory, one thing that is very important is that, everybody, okay? One thing that is very important is that this is what is important. Take a look at it. The metal and the ligand bond is considered to be ionic. What is it considered? It is considered to be ionic. Am I making myself clear? Okay, in this case, for the crystal field theory, it is considered to be the metal and the ligand bond. How many of you remember the metal and the ligand bond? Do you all remember that it was something like this? There was a metal, there was ligand. So this bond right here, this is considered to be ionic, okay? And it is said that it only arises because of the electrostatic forces, alright? Okay, everybody. Now, even before we understand, or even before we start with crystal field theory, how many of you know that the d orbitals are very important, my dear students, here, okay? The d orbitals are absolutely important here. So how do we make this d orbitals? Don't we make it something like this? We always write it like this, right? 1, 2, 3, 4, 5, right? Don't we always write it like this? Correct, everybody? D orbitals are always written like this. Now that means that we also have to give them names, right? We can't always say the first one, the second one, the third one. We can't say like this. It's just too much. So what name should we give them? What name should we give them? Any idea? What name are we giving them? Huh? Any idea? So first we will read about the octahedral complexes, then we will read about the tetrahedral ones, okay? Alright, so we are giving them some names like this. Let's move ahead and let's try to understand this, okay? Here. Okay, these are the names that are given to it, okay? So there is dxy, there is dyz, and there is dxz, okay? Now these ones, these are called as non-axial. What are these called as? These are called as non-axial. What do you mean by this word axial? Everybody, what do you mean by this word axial? How many of you know that the earth rotates on its axis, right? We always say that the earth is rotating on its axis. What do we mean by that? We mean that if this is the axis, then the earth is rotating on this. It's spinning on the axis, correct? It's spinning on the axis. Yes? Right, everybody? Correct? Now tell me something. It is spinning on the axis here. What if the axis was here and the earth was here? Then will you still consider this to be rotating on the axis? Will you still consider that this is rotating on the axis? Not at all. You will not be considering that. That means that here also, one second, let me erase it. Okay. Now that means that here also, as you can see, if I make it like this, that means the lobes are here. It's not falling on the axis. It is not falling on the axis. Do you see? It's in between the axis. It's in between the axis. Can we see it? Do we clearly see that, everyone? Yes, we do, right? Yes, we do. All right. Now let's take a look at it, everybody. Now let's take a look at it. So here dxy, that means it is in between the x and the y plane, okay? Miss, when will the class for 11? It will keep happening, Isaki. It will keep happening, okay? Don't worry, don't worry, don't worry. No problem, Picose, BGM, I will let you know about that. Thank you, NEET undergraduates. My health is much better now. I can take classes. But I am really waiting for the holidays. Maybe I can rest and then I will get back. Kaushika, I'll tell you, bacha, give me some time. We will come back to it, okay? We will come back to it. Don't worry. We will come back to it, alright? Don't worry. 1 second. Give me some time. I'll tell you that. Now, do you see that these are in between? So, these are non-axial. Is this clear, everyone? Is this clear that these are all non-axial? Yes. Hi, Dhanya. How are you? Yes. I will, bacha. Pehle, please consider here. Okay. Please focus here. We will talk about that in some time. Okay. Please focus here first. This is very important. Okay. To understand crystal field theory, which is the big boss of this whole chapter, it's very important that we study this. Also, I have mostly seen that many students, they find it very tough, but it is not going to be tough after this, okay? So, can we please focus here, everybody? Great. Now, so this is non-axial, everyone. Can I get some thumbs up, everyone? Yes, do we understand this? We do. Great. Now, do you see that this one, it is right on the z-axis? Do you see? Yes, if I write it like this, then do you see that it is right on the axis like this? Yes, and then there is a donut right here. Correct, everyone? Correct. This is right on the axis. So, what are we going to call this? We are going to call this axial. Correct. We are going to call this as axial. Am I right? So, these two, dx square minus y square and dz square, these are axial. Am I clear? So, there is non-axial and there is axial. Correct? Are you Tamil? No, I am not Tamilian. I am a Bengali. Okay? Alright. So, these are your d orbitals in octahedral feet. Now, tell me something. How many of you have watched this movie, Don't Look Up? Have you watched this movie, Don't Look Up? Jennifer Lawrence and, what is it? Leonardo DiCaprio's movie. Have you watched that movie? Anybody? And have you noticed that something is about to bombard the earth and everybody gets like crazy excited, like, oh my god, what is going to happen to us? Have you seen that? Come on, guys. Please. No. Acha, chalo, okay, all right. If you haven't watched that, no problem. Let's talk about something else. Yeah, let's talk about. Let's say some relatives are coming to your house. Some guests are coming to your house and they are going to stay at your house as well, okay? They're going to stay at your house as well. So what are you going to do? What are you going to do? Are you going to just sit like nonchalantly and you're like, yeah, so they're coming, big deal? Are you going to be like this, or are you going to start preparation? Okay, you are going to start preparing like, okay, we're going to have this dish, we're going to go here, we're going to go there. You are like full on plan and everything. So you are excited, right? You are excited. Now the same thing happens here also, my dear student. Take a look at it. If this is the metal here, if this is the metal here, right? These are the outer orbitals here. These are the outer orbitals, or let's say that these are the d orbitals here. Okay, so Kaushiki, do you understand here? Yes, do you understand here? Aren't we talking about the D, 3D, 4D, 5D series? The d orbitals are the outer, you know, the d orbitals are where the outer electrons are, Kaushiki. Yes, did I answer that? See, I answered that, right? So here are the d orbitals. Now, let's say that the ligand is approaching here. Yes, the ligand is approaching here. Now tell me, do you think that all of them are going to be very happy and nonchalant? Like, so what if somebody is coming? Big deal. Why am I bothered? Will I be bothered? I will be. These guys also have electrons, right? These guys also have electrons, and this is also going to approach. Obviously, there will be some repulsion and they're not going to like everything, right? They're not going to like everyone from that whole family equally, correct? Now let's just imagine, so first what happens is, from here they were all chilling and all, right? These d orbitals, they were all chilling, like, okay, fine. Life is all cool, they are fine. But then suddenly the ligand approaches. Now the moment the ligand approaches, they are all excited. See, they have moved up, so they have gone to the excited state. They are all excited now. Now after getting excited, let's say that there is the parents, mom, dad, and you know, let's say an aunt. So obviously, normally what happens, mom and dad, they have their own room, and the aunt also gets her own room. But the kids, you all are asked to share your room with your cousin maybe, and let's just say that you have a PS2, you like playing with the PS2 whenever you are taking a break from your studies, and you have only one controller. But that cousin who is coming, he or she also is like, you know, or even I love PS2 and I have to play with PS2 right at the time when you are playing. What will happen? Both of you will start fighting, right? Both of you will start fighting and you will be like, this is not working out. This is not working out and you are not liking. So what will happen? So the mom, dad and the aunt, they have settled down. But here the cousin or the siblings, what happens? They are even getting angrier. They are even more excited. They are like, no dude, what are you doing? PS2 is mine. You have come to my house. You should play by my rules. But your cousin is like, but I am guest. I need to have the PS2. So what happens? They get even more angry and they go here. Now try to use the same analogy here, okay? Now try to use the same analogy here. Take a look at this, everyone. I'm going to remove this from here. Take a look at this. Yes? So we all know that when it is so again, take a look at this, octahedral field, okay? We are talking about octahedral field. So that means that there is a metal, ligand. Yes. Now what will happen? They are directly coming to this head, okay? They want to sit on top of your head and they are like, no, I have to play with the PS2. I need the PS2. So what will happen? Super angry, bro. Very angry they are. And now they have gone here. So we call them EG, okay? We call them EG and here we call them as T2G. Is this clear, everyone? How the splitting is happening? How the d orbitals are getting split? Do we understand this, everybody? Can I get some la 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 or a thumbs up? Anything will do, everybody. Please come on, tell me quickly. Do we understand this? Yes, this is clear? Great, okay? Now, I'm so sorry, Swatika. I'm so sorry. Like I told, my health was not well and you know, yesterday there was a huge hustle bustle of everything going in the office and I just couldn't take class, so I had to postpone it, okay. But anyway, after we complete this, then we are ready for P block. So after that we will be reading about P block, and P block is going to be very easy because we are already done with the periodic trends and we will be done with this, okay. So it's going to be very easy, don't worry about it, but that will be recorded, that will not be live, okay. Alright everybody, chalo, moving on. So we understand. Now, the difference of energy between the two sets of d orbitals, what is this called? Any idea what is this called? This is called as your CFSC, that is crystal field splitting energy. Okay? Crystal field, sorry, I was reading the chat. Yes, crystal field splitting energy. Now that is given as minus 0.4 plus 0.6 NEG NT2G delta. You're going to ask me, ma'am, where is this number coming from? How many of you have this doubt? Come on, let me see how many of you have this doubt that where are these numbers coming from? How many of you have this? Dhanya, I'm better. I actually had, I think, kind of like stomach infection or something. So yeah, that's why. Aishu, you have the doubt. Very good. Let me tell you now. Okay, let's see this again. See, this is your center, right? This is your center. Now in d orbitals there are 5 orbitals, correct? There are 5 orbitals. So let me write it as 5. I take it as denominator, okay? Now these electrons, they are settling down. These orbitals, they are settling down. They are stabilized. They came back, okay? They came back from the excited state because of these two. Am I right? These two are at a higher state, but these two have come down. So because of these two, or among the 5, these two are up, but these 3 have come down. So can I write, but then again they have come down, see, they are at the bottom. Yes, they are stabilizing. So can I write it as minus 2 because of this 2 here, these 3 are lying down, correct? So can I write it as minus 2 by 5 delta? Oh, now tell me what is the value of this. Now tell me what is the value of this minus 2 by 5. Tell me. Minus 2 by 5. Quickly calculate it and tell me. What will it be? What will it be? Minus 2 by 5, will it be equal to 0.4? Will it be equal to 0.4? Yes or no? Guys, can we please make it a little more interactive? Please talk. Yes, Aishu. So that's where we get it. Minus 0.4 delta O. Same thing here also. Denominator 5. Because of this 3, here these 2 are up. So 3 by 5 delta O. But this one went up. So this will be positive. Now what will be 3 by 5? Calculate this. What will be 3 by 5? Calculate this, everybody. Yes. I'm very bad at mathematics. You will have to tell me that. You will have to tell me that. I'm very bad at mathematics. Very good. So this becomes 0.6 delta O. Yes. So now are we clear? Why, from where does these numbers come in? From where does this number come in? Who is writing? Swatika, no, it's not going to be minus 0.6, bacha. It is since it is going up, it is going to be positive only. Okay. So there is CFSC is equal to minus 0.4 and T2G. Did you see that these are the T2G ones? Okay. These are the T2G and these are the EG ones. Right. So can we now consider this formula? Does this formula make sense now? Yes. Does this formula make sense now? Clear, everybody? Great. Now crystal field splitting energy, what does it depend on? What does it depend on? Obviously there has to be some things that it depends on, right? It cannot be, okay, Aishu, for why T2G and all, for that we will have to, kind of do PhD on it. So let's not go into that right now. Please just remember that it is T2G and EG, okay? If we really have to know that why T2G and why EG, there are different names also. So we will have to really get into deep. We will probably have to do masters in science and all of that. Then we will get to know. So forget about it right now. Just remember it, okay? EG, T2G, okay? T2G, EG, alright? So crystal field splitting energy, what does it depend on? It depends on nature of ligand. It obviously depends on nature of ligand. Now imagine, what if the cousin that is coming in is very volatile? He wants to break things, okay? He wants to not sit at home. He wants to do this thing and that thing and all of that thing. Will you like him? No. Will you like him? No. the more angrier you will get, right? Yes, more angrier you will get, because if you have someone like that, you will be like, no, I am not gonna stay with that person. Yes, so the splitting will be more. The splitting will be more. But if it is a weak ligand, if the cousin is like, oh, okay, no problem, it's absolutely fine, all cool, we will deal with it, we will sort it out among ourselves, then what will happen? The splitting will be less. You will be like, okay, not so much of problem, it's fine, it's cool. So, if there is a strong field ligand, then obviously the splitting will be more. And if it is a weak field ligand, then the splitting will be less. Correct? Yes, bacha. Yes, absolutely right. Yes. See, more splitting, delta O. Yes, do you see this? They will pair up the electrons. Now, can you remember? Now, because please do not do this, sweetheart. Let me teach now. We will answer your doubts later. Okay, please concentrate here. It's very important that you study this, and if you know it, just stay quiet. Okay, all the other students, they are learning probably for the first time. Is that okay? My dear bacha, please do that. Okay. Yeah, so do you this. Now do you remember in valence bond theory, we could not predict it, that why are they pairing up or why are they not pairing up. Only after looking at the magnetic moment, we are still confused that this is just not making sense. In valence bond theory, in fact, in valence bond theory, you always needed an extra information. But here, from this, you can easily predict, right? So, strong field ligand will try to pair it up, whereas a weak field ligand, they will not be able to pair it up. Okay? They will not be able to pair it up. Correct? Correct, everybody? So, that means that the strong field ligand and the weak field ligand, now we have to know who are these. We will have to know who are these, right? And that series where the weak ligands to the strong ligands, there is a series which is called as Spectrochemical Series. Okay, it is called as Spectrochemical Series. Am I clear? Somebody asked me in the last class, ma'am, when are we going to do Spectrochemical Series? See, here, I did it right now. Is this clear? Is this clear? Should we remember it? Yes, I think you should, but it's okay. I think you will be able to easily remember it. See, I, Br, Cl, F, all of these are what? Halogen. All of these are halogen, correct? So, they are all weak ligands, okay? They are all weak ligands. But here if you go see Cn, Co, NH3, okay, these are all strong ligands, alright? So, if you just remember this much, it's easy. Just remember this much. Halogens, weak ligands, they don't have the strength. They are alright, okay? Whenever they come, they are like, okay, we will deal with it, no problem. They are fine with it. So, these are the ones that are weak ligands, and if you just remember this side, it's okay. It's alright. That much you can do, okay? Narayana Sai, you don't really need a trick. If you just remember that these halogens or, you know, Cl minus, F minus, Br minus, I minus, these are the weak ligands, okay? Whereas NH3, Cn minus, Co, these are the strong ligands. That much is enough. More than enough. Do we understand this, everybody? Yes? Okay. So, this is the Spectrochemical Series, alright? Whoever asked me that, I can't remember that kid's name, but please do let him know that ma'am has done Spectrochemical Series already, okay? Ma'am has taken care of Spectrochemical Series already. Moving on. Take a look at this. See, if it is a weak field, H2 is also a weak ligand only. H2 is also a weak ligand, but not that strong also, it's fine. It's an okayish ligand, okay? Now take a look at it. See, if the weak, this is an example here. See, if there is a weak field ligand like, see, fluorine, what will happen? It is very less. The splitting energy is very less. But if it is a strong field ligand like Cn, take a look at this. Take a look at this. How much it is? How big is the splitting energy? Acha, now tell me something. Let's say that it is D6. D6 in weak field ligand. Tell me how the electrons will fill up the orbitals. Anybody, any idea? Anybody, any idea? D6 in weak field ligand. Tell me. Tell me. Swatika will come to that, bacha. Don't worry, okay? We will do everything. Don't worry about it. All of these questions will come. We will build it one step at a time, okay? Tell me. No pairing. D6, are you sure? Omar, think about it. what will happen? D6 in weak field. Okay, let's do this. Okay, so here you have 1, 2 and 3, let's say. Let me make this a little better. Let me make this a little better. Okay, so D6. Okay, let's consider it here. So here I have 1, 2, 3 and here I have 1 and 2, right? D6. So there will be 1, 2, 3. All right. Now, because the energy gap is not so much, what will I do? I would rather take this empty one. So 5 is already filled, but here they will be, right? Here there will be, one will be paired, right? One orbital will be pairing, right? Exactly, Ashwin. So how do we write it? We will write it as T2G4, okay? T2G4 Eg2. Very good. T2G4 Eg2. Is it buffering? Shabazz, is it buffering? Incorrect. Ashwin, T2J4 Eg2. Very good. Exactly. Yes. Now tell me, let me write it down once again. Tell me D8. Okay. Tell me D8 in strong field ligand. Tell me. Tell me this. D8 in SFL. Come on. Go ahead. Let me see how many of you can do this. Come on, come on, come on. Ashwin is the only one who is giving answers. Huh? No one else. No one else is giving me answers. Very good, because the splitting energy is so much. So 1, 2, 3, 4, 5, 6, 7, 8. Exactly. So it will be T2G6 Eg2. Very good. T2G6 Eg2, bacha. Jeevashri. 8, no? 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? Alright. Got it, everybody? Is this clear? Awesome. Alright. Now let's go to splitting in tetrahedral field. Okay? Shall we go to tetrahedral? Is octahedral field absolutely clear? So if there is any question from crystal field, will you be able to answer it? Is it very easy? Is it very easy? Yes. Now let's go to splitting. Okay? Alright. Now let's go to splitting in tetrahedral field. Acha. So in octahedral field, we saw that the axial ones, they were very excited and they were very angry. So they went up. But is that the same case in tetrahedral field? No. Actually, no. In case of tetrahedral field, it's actually the ulta, it's actually the opposite. So here what happens, you can see that the non-axial ones, they are getting scared. They are like, oh my god, these people are coming. There are too many people who are coming. So what will we do? Now even the mom, dads and the relatives, relatives room is gone. No privacy there also now. Now they even also have to share. Okay, so what will they do? Now these guys are going crazy. So this dxy, dxz and dyz, they are crazy. Okay, they are crazy. Are you understanding? Yes. So now they are going to go to the higher energy. Okay, they are going to go to the higher energy. But these ones, the axial ones, they are fine. They are like, it's okay, no problem. So what if they are coming? We are okay with it. Yeah. They are absolutely okay with it. So they are going to come to the lower energy. They are going to come to the lower energy. So take a look at this. Here, see what is happening. Dx square minus y square and dz square, they are at the bottom now. And in the octahedral field, what did we talk about? We spoke that they were Eg and T2G. But now, right now, we are not going to call them as T2G and Eg. Okay. Right now, we are not going to call them as T2G or Eg. Why? Because even the splitting is not so much. Why to give them so much respect? Why should we add another letter? We'll just write it as E and T2. Okay? We're just going to write it as E and T2. So as you can see that the E comes at the bottom, whereas T2 goes up. Okay? T2 goes up. Are we understanding this? Are we understanding this, everyone? Getting it? What is happening in tetrahedral field? Getting it? Now same thing here also. What happens is minus 0.6. Why is it minus 0.6? Because see, this came down. This came at the bottom. Stabilization happened. Stabilization happened. Yes. But here what happened? 0.4 went up. 0.4 went up. Yes. Do you see? 0.4, sorry, I'm going back. See, 0.4 went up. So here this becomes positive. So that's the formula. Yes, that's the formula. Shabaz, I think you were not there since the beginning. So sweetheart, why don't you go and watch it from the beginning, okay? Once the class is over, please watch it from the beginning so that you understand everything. Got it? Alright. Now let's understand what are the factors that affect this CFSE. What are the factors that affect this energy, right? Let's understand strength of the ligand. Strength of the ligand. Obviously, which we already just spoke about, right? So CFSE is more in case of a strong field ligand as compared to weak field ligand. Right? Okay? Okay? Alright. Now, oxidation state of central metal ion. This is also very important, my dear student. Okay? CFSE is directly proportional to oxidation state. So, if I have, let's say, there is one metal at +2 state and one metal at +3 state, which one will have more CFSE? Which one will have more CFSE? Come on. Please, please, please go. Tell me. Which one will have more CFSE? I've actually noted it down already. It will be +3, right? The +3 oxidation state will have more CFSE, alright? Then also the transition series, the D series, they also affect it, okay? Take a look at it. The 5D will have more splitting, 4D will have a little less and 3D will be even more less. Why? Any idea? Take a wild guess and tell me. Take a wild guess and tell me why is it that the CFSE get affected by this 5D, 4D and 3D? Why? Any idea? Please, go ahead. Take a wild guess. I want to see the answer. Come on. I want to see the answer. Oh my God, Aishu, very good. Clap for yourself. Very, very, very good. Absolutely right. It is, yes, the shielding effect. Don't we remember, as we keep going down the group, what happens? The electron, the nucleus is able to pull the electrons more. So when they are trying to pull the electrons more, don't you think that the ligand will even strongly approach this? The ligand will even strongly approach this, and when it tries to strongly approach this, what will happen? The d orbitals, they will go even more crazy, right? They will go even more crazy, and that's why the splitting will also be more, right? The splitting will also be more. Do we understand this, everyone? Is this clear? Is this clear, bacha? Yes. Also the geometry number of the ligand. Take a look at it. The square planar has the more, then comes octahedral, and then comes tetrahedral. Now how do we relate this? Yes, how do we relate this? Ashwin, no ma'am, I can't understand, sorry. Polomi, very good, bacha, very good. Congratulations to you. Yes? Very good. Okay. Well, can't understand. Huh? Ashwin, okay, do me a favor, sweetheart. Do me a favor. Let's not, take more time into this chapter, because we already have taken a very long time to complete this chapter. So what I'm gonna tell you is, please listen to me, Ashwin. I have already taken care of periodic trends, okay? I've already taken care of periodic trends as well as periodic exceptions. So if you do not mind, please watch those two videos. Right in the beginning, when I came into this channel, I took these two chapters, okay? I took these two videos. Please watch them so that you can understand this shielding effect, the effective nuclear charge. I have explained all of it very clearly. Okay, in fact, there was this one video where I said that I'll be taking periodic trends in just half an hour, but I couldn't complete it in half an hour. It went for 1 hour, okay? Yes, it went for 1 hour. So please take a look at that, Ashwin, okay? You'll be able to understand. Now, please try to remember this, okay? Please try to remember this. This I'm not going to go through details right now because it will take me a long time. So please remember this. After finishing all the one-shots, okay? After finishing all the one-shots of inorganic chemistry, I will go into each and every topic again elaborately. Because I know that your NEET exam, your JEE exams are quite far away now. So if you start from now, once if you complete your syllabus, and after that when you see all of these, everything will be like, now we got it. So please just remember this right now, okay? Please see, delta SP, that is square planar, is equal to 4/3 of delta octahedral, okay? Please remember this. I'm going to ask you one question right now. I'm going to test it right now, okay? Remember this. Delta tetrahedral is equal to 4/9 of delta octahedral. Okay, yes, I will do P block also. Okay, I will do P block also. Then delta Sp is equal to 1.3 of delta octahedral. Now, my question is, tell me, the crystal field stabilization energy, that is CFSC, for COCl6 4 minus is 18,000 per centimeter, or Cm minus 1. Okay. Now, the CFSC for COCl4 2 minus will be, calculate. I've just given you the, just showed you the formula, and this is a previous year question from NEET 2019. Tell me. Jeevashri we will see, bacha, we will see. Okay, see, right now I'm only taking inorganic chemistry, so let's complete every chapter first, and then we will come back to it. And you know that Wasim sir is taking care of your physical chemistry and organic chemistry, right? Are you sure? Captain Jack, how did you calculate it? Tell me. See, it is given as, see what it is given as. COCl6 4 minus is 18,000. The CFSC for COCl4 2 minus will be, all of you are saying A. But the answer is 8,000, option D. Let's see how we calculated it. See, delta T is equal to 4 by 9 of delta O. Yes. Now, delta T was given. Delta T was already given to you. Oh, sorry, delta O was already given to you. Take a look at it. See, CL6 was already given to you. So, all you had to do was 4 by 9 into 18,000 and you would have got this number. Did you understand? Did you understand? Take a look at the question one more time. See, the crystal field stabilization energy for COCl6 4 minus is 18,000. Okay. There are 6 ligands. There are 6 ligands, and 6 ligands will only be possible for octahedral. But here there are 4 ligands. That means it is tetrahedral. Yes, Aishu. Cl6, where is it possible? How is 6 ligands possible? 6 ligands will only be possible in octahedral, no? How will, in tetrahedral, how will you fit the other 2? You can't. You cannot, right? So, Cl6 is for octahedral here. This is for tetrahedral. That's it. That was your hint. Is this understood? Is this understood, everybody? Now, let's move on towards isomerism. But before isomerism, we also have to do color of coordination compounds. Now, tell me something. Was valence bond theory able to explain this? No. Valence bond theory absolutely failed in explaining this. It just couldn't. It just couldn't, right? And that's why we needed a newer theory, which is why we have the crystal field theory. So, color of coordination compounds, let's understand this. How do we understand this? Okay. So, why does this color even arise? Why is it that the color is there? The color is there only because of the DD transition. Okay. DD transition. Now, tell me something. What if there is no ligand? Will it show color? What if in a compound there is no ligand? Will it show color? It will not show color. It will not show color. If it is D0 and D10, will it show color? D0 and D10. It will not show color. It will again not show color. Okay. Alright. Due to DD transition, Mohan. Due to DD transition. Okay. Now, what are the colors? The colors, hey, we all know it is those 7 colors, Vibgya, right? It is always Vibgya, correct? Now, let me tell you the trick. So, if the energy gap is less, then the wavelength is more. If the wavelength is more, then it will show a reddish color tinge, okay? A slightly reddish shade will be shown by the compound. But if the energy gap is more, then the wavelength will be less, and at that point of time, the compound will show you bluish. That's it. That's your color of coordination compound. That's it. Nothing else you need. Nothing else you need. Okay. So now, can you tell me if it is a strong field ligand, what will you get? The energy gap will be more. So what will be the color of the coordination compound? Come on, Mohan, tell me. What will be the color of the coordination compound? If it is a strong field ligand, then what will happen? I'm not seeing any replies, guys. Blue. Very good, Captain Jack. Thank you. Very good. So is this clear, everybody? This is very easy. We just have to remember this trick. Okay. No. Jeevashri. No. Take a look at it. Huh. Violet. Aishu, no. Okay. Again, one more time, everybody. One more time. Let me explain this to you one more time. Okay. See, if at all the energy gap is less, that means the splitting is less. If the splitting is less, then the wavelength is more. Okay. Then the wavelength is more. If the wavelength is more, then the shade of the coordination compound will be towards red. And if the splitting is more, if the energy gap is more, then the wavelength will be less, and that is why the color will be towards blue. So I asked if there is a strong field ligand, that means the splitting is more. If the splitting is more, energy gap is more, that means wavelength is less. So that means it will be blue color. Right? Now did you understand? Now did you understand? Tilagavati, did you understand this now? One trick, that's it. Very simple, one trick. Energy gap less, wavelength more, reddish. Energy gap more, wavelength less, bluish. Yes? Got it? Pakka clear? Can I see some thumbnails? Can I see some thumbs up? Can I see some thumbs up, everybody? Yes? Okay, great. Now then moving on. So now let's complete isomerism. Once isomerism is done, this chapter is over. See, we are almost done. We are almost done. So now what is isomerism? Okay, I want to see the answer. I want to see the answer. What is isomerism, Baba? Tell me, what is isomerism? How many of you know what is isomerism? Hi Rakiba. Welcome. Hi Singham. Arey, why are you all so late? You guys did not know about that I had class. I even posted it on this thing. I even posted it on Telegram. Similar structure. Very good. Okay, that's right. So isomerism from where? Very good, Aishu. Very good. Isomerism is basically two or more chemical compounds which have identical formula, but the arrangement is different. Right? Yes? We didn't get it. You didn't check the Telegram group. You didn't check the Telegram group. Isomer of carbon. No, graphite and diamond are not isomer, they are allotropes. What are they called? They are called allotropes. Okay, they don't have the same formula. All right, they don't have the same formula, sweetheart. Mohan, that's a misconception. Very good. Yes. Say na. Acha, no problem. Chalo, theek hai. But anyway, share it with your friends. Okay, share it with your friends. Same arrangement. No, Jeevashri, they have the same chemical formula, but they have different structures. Now, obviously, based on that, once again, see, they have the same molecular formula, but the arrangement of the atoms is different. Okay, arrangement of the atoms is different. So, take a look at it, Bacha. The easiest example is your hands. Both of your hands have the same number of fingers, right? Both of them almost look equal. But even if I try to overlap them, I will never be able to, right? It forms a fish, see? It's different. The arrangement is slightly different. Correct? Are you understanding this? So this is your isomerism. This is your isomerism. However, there are different types of isomerism, right? There are different types of isomerism that we are going to understand now, okay? Now there is, broadly, if you want to classify, then you can classify it as structural isomerism, and you can also classify it as stereoisomerism. Okay, now stereoisomerism is all about space. I'll give you a very funny example. Have you ever noticed that, let's say that two people are standing and talking. It is dark and they are probably standing near a drain. Have you seen the number of mosquitoes that are right above their head? Yes. Now both of them are standing right there and both of them have mosquitoes, but the way the mosquitoes are arranging there, they'll be slightly different, right? In the space, they'll be slightly different, isn't it? So that example is probably for stereoisomerism. Yeah, that example is probably for stereoisomerism. Every time somebody says stereoisomerism, just remember that mosquitoes are right on top of the head, okay? Alright. Anyway, now coming to structural isomerism. Structural isomerism, sweethearts, can be divided, can be divided into 4 groups. Okay, so there is same chemical formula but different bonds. All right. Same chemical formula but different bonds. So there is ionization isomerism, there is hydration isomerism or solvate isomerism, there is linkage isomerism, and there is coordination isomerism. All right. So let's talk about it, everybody. What is this ionization isomerism, everybody? What is this ionization isomerism? Take a look at it. Very easy. See, do you see that SO4 right here is inside the coordination sphere? Let me come here. See, SO4 is inside the coordination sphere, but in the next one SO4 came out, it became counter ion. But if you take a look at it, both of them have the same compounds. Both of them have the same compounds. Do you see? Do you see, everybody? Yes. In one of this, you see that SO4 is inside the coordination sphere, but what is happening? In here, it has become the counter ion. Nothing but this is the one. Nothing but this is the one. This is your ionization isomerism. Clear? Just by one, just by looking at one of the examples, you can understand. It's very easy. Isomerism is very easy. In fact, you also read about isomerism in organic chemistry, right? Yes. You also read about isomerism in organic chemistry, isn't it? Yes? Correct, Mohan. Yes, it occurs due to exchange of counter ion and ligand. Yes, absolutely right. Oh, thank you, Sanjay. Thank you so much. All right, moving on. Let's go to. Acha. Now, somebody might ask you that how will you understand that these ones have the same compound, but they are, there is ionization isomerism. How will you do this? How will you understand? Aisha, this is just metal and ligand bonding, Baba. This is only because of metal and ligand bonding, okay? It's their wish, however they want to stay. All right. So what we will do is, you have those sulfate, nitrate tests you have, right? You have those tests, right? So the same way, if we want to test for sulfate, what we will do? I'll just add barium chloride. If I add barium chloride to both of them, I will see that I'm getting white PPT only in this case. I'm getting white PPT only in this case. When the sulfate ion is the counter ion, only at that time I'm getting white PPT. Now why? Why am I getting it only for this? Why am I getting it only for this and why am I not getting it for this? Because if you remember Werner's theory, what did Werner say? That this one is ionizable. Yes, the counter ion will separate out and show its colors, but whatever is inside the coordination sphere, that you might not even see. So see, here the sulfate is going to give you the positive test. Yes, sulfate is going to give you the positive test. Very good, Aishu, but in here sulfate is not free. But in here, if you add silver nitrate, you will get pale yellow PPT, but in here you will not get that. So that is how we can test, okay? That is how we can test. All right? Yes? How to find which compound is which? I'll show you. See? Do you understand ionization isomerism, Mohan? Did you understand this? The moment you look at it, you will be able to understand after this. So if you have two types, if you are given two options like this, you will just take a look at it and you will understand that this is ionization isomerism. All right? Moving on now. Moving on. Okay? Moving on. Now let's understand hydrate or solvate isomerism. What is this now? What is this now? Take a look at it. See, again, this is also all about the H2O. All about the H2O. In here, water is inside the coordination sphere, but in here, water is out. In here, water is out. So, if the water is inside the coordination sphere, you will get violet color, but if it is outside, you will get a grey-green color. So the moment you see that in one of them H2O is inside and in one of them it is outside, you will be able to say that it is the hydrate isomerism. Yes, you will be able to say that it is hydrate isomerism. Am I correct, everybody? Am I correct, everyone? This is clear again? Is this clear? Just by looking at it, you can understand? Yes, it's all because of aqua. Yes, all because of aqua. Yes, absolutely, Bacha. Absolutely, Mohan. You are right. You are right. Okay. All right. Okay. Now we come to the next one. Next one. Take a look at it. Next one. This is your linkage isomerism. Okay. What is this linkage isomerism? What is this linkage isomerism? Okay, now tell me something. I have two hands, right? I have two hands. If you ask me that, ma'am, you have two hands, pick up the bottle. Pick up the bottle. What will I do? I can either pick it up with my left hand or I can pick it up with my right hand. Anything. Both of the hands work. Both of them work. I can pick it up with anything. Right? The same way, the very same way, take a look at this example. See, NO2. NO2. Okay? And there is ONO. So what is happening? At certain point, the ligand is attached to the metal from the nitrogen side, or it can be attached through oxygen. See, it has two donor sites. It has two donor sites, and this happens due to ambidentate ligands. Write it down, okay? This happens due to ambidentate ligands. All right, got it? Yes, see, it has two donor sites. So whichever one it wants, whenever it wants, however it wants, it's the ligand's wish. So this is called as linkage isomerism. All right, this is called as linkage isomerism. Thank you, Nihil. Thank you so much. Is this the lecture? Is this the last? Yes, for now, modern man, I'm only trying to complete the one shot so that at least for once your syllabus is absolutely complete, and you can, whatever exams you are giving, any competitive exams you are giving, you know that you can answer, okay? You can at least attempt the questions. However, once we finish all the one shot, we will come back again and we will do all the topics elaborately one more time. Is that okay? All right, that's my plan, okay? That's my plan regarding it. Anyway, now, do we understand this? Again, this will also have two different colors. Okay, this will also have two different colors. Now we come to coordination isomerism, and this is the last one for structural isomerism. What is this? What is this? This is like, let's say there are two students in the class. There are, okay, let's say that there are two siblings, okay? Two siblings or two twins. Two twins in the same class, both of them have the same bag and both of them have the same geometry box. So one fine day what happened was, let's say that Ram and Sham, okay? Let's say Ram and Sham. So Ram went with Sham's tiffin box and Sham went with Ram's tiffin box. Yes, exactly. Just what is happening? The metals are, see, getting exchanged. Metals are getting exchanged. Do you see? So next time when you see this, you can easily identify that this is coordination isomerism. Yes, this is your coordination isomerism. Yes, Mohan, absolutely right. This is clear. Now let's take a look at it all. Look at all of them, everyone. Let's take a look at all of them, everyone. Okay. The first one was your ionization isomerism. Yes. No problem, Ashwin. After the class ends also, you can watch the this thing. Okay. Watch the replay. Okay. So in case of ionization isomerism, we saw that the ligand can be either inside the coordination sphere or it can act like a counter ion, okay? Or it can act like a counter ion. Yes, there will be PYQs as well, don't worry, okay? I will complete the whole inorganic, everything, end to end, don't worry about it, okay? Or otherwise, we have something called as hydrate or hydrate isomerism. What happens? Either H2O is inside the coordination sphere or it is outside acting like a counter ion, right? That is your hydrate isomerism. Next, what do we have? We have linkage isomerism, which occurs due to ambidentate ligands, okay? Either it can pick it up with left hand or it can pick it up with right hand, all right? That's your linkage isomerism. And finally we come to coordination isomerism, where we see that the metals are exchanged, right? Is this clear? Structural isomerism all clear? Yes? No? Yes or no, guys? Come on, tell me. Till then I'm gonna drink some water. I can't understand linkage. Okay, Aishu, one more time, bacha. See, I have two hands, Aishu. I have two hands. If you ask me, ma'am, pick up the bottle, what will I do? I can either pick it up with my left hand or I can pick it up with my right hand, right? Ashwin, it is omitted for NCERT, but you know that this channel also deals with JEE and NEET, right? It is there in JEE and NEET. What will you do? What will you do? We'll have to study, right? So I can either pick it up with my left hand or with my right hand. The same way, when a ligand has two donor site, right, NO2, nitrogen is also a donor site, oxygen is also a donor site. So either it can attach through nitrogen or it can attach through oxygen. That's it. That's your linkage isomerism. This happens only in ambidentate ligands. Got it? All right, everybody? Yes? Now, stereoisomers. In case of stereoisomerism, we again have two types. Stereoisomerism example, what was it? What was the example of stereoisomerism? Remember, two people standing there, both of them have mosquitoes above their head. What happens? Spatial arrangement of mosquitoes are not same. Although both of them have black hair, both of them are wearing black clothes and they are standing right in front of the train, they have mosquitoes on top of their head, but the spatial arrangement of mosquitoes are not the same, right? Possible? Exactly. So we have geometrical isomerism and we have optical isomerism. So let's talk about the geometrical. Do you all know about the cis and trans isomerism, guys? We all know about the cis and trans isomerism, right? Yes. So this geometrical isomerism or the cis and trans isomerism, it is usually shown by your square planar complex or it is shown by the octahedral complex. So let's take a look at it, okay? For square planar, what will happen is if it is Ma4 or let's say that if it is COCl4. If it is like this, then this will not show you. This will not show you. What happened to this? Oh, this has come here. This is not going to show you the isomerism. Clear? Alright. But Ma2B2, if there are two different types of ligands or there are three types of ligands or all the four are different, you will get to see the geometrical isomerism, okay? But if it is Ma4, why? Okay, tell me something, Aishu, why? Let me explain this. See, CO, Cl, 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 okay? And then let's say that, this is annoying. See, tell me, aren't all of them same, Aishu? You tell me, how will the geometrical geometrical isomerism be visible? You tell me. All of them are same, no? Rotate it, still see the same. Rotate it even more, it will still be the same. Rotate it even more, it will still be the same. There is no difference. Right, Aishu? Do we understand this now? Why it will not show you? Yes, that's it. Okay, that's it. Just imagine the 3D effect. You will be able to get it clear. Okay, all right, moving on. But these three will show you the geometrical isomerism. This is easy, very good. This is absolutely easy. Well done. See, if I have Ma2B2, what will I get? See, if it is PTNH32Cl2, what will I get? This is how it will look. So either you will have cis, where see, these two are on the same side, or you will have this, which is your trans, right? All right. Ma3, I'll show you, don't worry. I'll show you. Do you understand this? PTNH32Cl2, yes, cis and trans, yes, correct everybody. Now Ma2BC, so there are three different ligands, see, PTNH32ClNO2. How will it happen? See, cis. What is happening? NH3, NH3, cis. NH3, NH3, trans. Yes, this is going to show you geometrical isomerism. Now MABCD, okay, this one can show you three different types. This one can show you three difference. Take a look at it. See, either it can be like this, Cl and Br. Okay, this is going to be your cis. See, pyridine is on the top, NH3 is at the bottom, or it can be NH3 at the top, pyridine at the bottom, and ClBr cis, and there will be a trans also. Cl and Br on the opposite side, there will be a trans also. Understanding? Yes, this is clear, very easy everybody. Now let's come to octahedral complexes. For octahedral complexes, again see Ma4B2, Ma2 or BB2 or Ma3B3. you will get the geometrical isomerism. But for this Ma6 or Ma5b, you will not get it. You will not get it. Yes? Do we understand this? Do we understand this? Let's take a look at it. Ma4b2, CrNH34Cl2 plus what is happening? See, either it is cis like this, Cl, so cis here, okay, or it is going to be Cl and Cl, so this is your trans. Yes, this is your trans, correct? Moving on, Ma2BB2, okay, what will happen? See, COCl2En2. Yes, this is what? You know this? You know this? Now take a look at it. Singham, your answer. Your answer, bacha. See, either it will be cis or it will be trans like this. That's it. That's it. Singham, you got your answer, right? You got your answer. Whatever you just asked, see, this is where your answer is. Alright, now it is Ma3B3. Okay, CONH3, 3NO2, 3. This again, oh, this is interesting. This is interesting. Yes, it is facial isomer. Okay, so what do we call it? We usually call it as Fekmar Isomer. Okay, what do we call it? Fekmar Isomer. Take a look at it. Either it will be all the three similar ones are here, and again all the three similar ones are like here. Okay, so this becomes your facial. Or either if you just change one of the arrangements, you will get Mar isomer. Okay, you will get Mar isomer. This is also clear, everyone. All right, this is also clear. Now these complexes, they have which have same physical and chemical properties, but they differ in their action towards plane polarized light. They are called as optical isomerism. Okay, what are they called? They are called as optical isomerism. So you know that dextro, levo, how they rotate? Yes, how they rotate. Aryan bacha, you will have to see the first one. Please watch the first one, okay? Watch the first coordination compound. Do not miss the classes, bacha. If you miss the classes, then you will not understand like this, okay? Aryan Yadav, please watch the first one. You will be able to understand, okay? Anyway, so optically active complexes. How many of you have heard this? How many of you have heard this? Oh, it's been only 1 hour, no problem. We'll just complete it now. It's about to be over, okay? Yes, they are the dextro and levo. So this, your hands are your dextro and levo, okay? Your hands are your dextro and levo. You see that they are mirror images. They are absolutely mirror images. But if you try to overlap them, they are not going to get overlapped. They are not going to get overlap, okay? So dextro D, what it does is it rotates the plane polarized lights towards the right side, okay? The levo ones, what they do is they rotate the plane polarized light towards the left side. Take a look at it. The this dextro and levo isomers, no, they are called as enantiomers or enantiomorphs. Again, this you have learnt it in organic chemistry a lot, right? In organic chemistry, whoever has done their organic chemistry very well, you will definitely remember this, right? You will definitely remember this. Correct, everybody? Yes? Do we understand this? See, again they are shown by tetrahedral complexes and octahedral complexes. Yes, Captain Jack, absolutely right. Now tell me, why square planar complex does not show optical isomerism? This is my question to you. Tell me. Why is it that square planar complexes, they do not show optical isomerism? Answer. Till then I am going to drink some water. This is my break. Any idea? Because this is how it is. Square planar has a complex plane of symmetry, so it will not show, okay? Now for tetrahedral complexes, only MABCD will show you the optical isomerism, okay? MABCD, they will show the optical. Very good, everyone. Very good, Rakiba. Okay, now for octahedral complexes, optical isomerism. Guys, we are talking about optical isomerism. Optical isomerism for tetrahedral, you will only see it in MABCD, okay? But if it is octahedral, then you will see it only cis forms. You will see it everywhere. See, MA2, B2, C2, MA, B, C, D, E, F, MAA3, okay, all right. Then you have MAA2B2 or MAAB2C2. You will see it in every which way. You will see it in every which way. So MA2, B2, C2 type. See, this is your example. It is PT, pyridine, NH3, Cl2, all of them are there. So what will happen? Here, you will have cis D isomer or you will have cis L isomer. Okay, this does not occur with the trans ones. Okay, once again, write it down if possible. Write it in a notebook. It is not possible for trans. Okay, it is only possible for cis. Am I making myself clear? All right. Guys, tell me something. Do you want me to start from even more basic? Because I did that in the periodic trends, and some of the students told me that, ma'am, don't take it from the basics. If you take it from the basics, then it's very time consuming, and you know, you have to, your time is the most important thing for you all. So the way I'm teaching, is this fine, or do you want me to start from the basic? Because I can do that. I really can do that. If you have any issues, we can really start from the basic, or you can just wait until I start teaching it elaborately. Okay, Singham, is this fine? Ashwin, try to concentrate. No time, ma'am. Okay, all right then. Okay, so there is MABCDEF type. Now see D isomer, okay, and this you have L isomer. See, mirror images, absolute mirror images. Do you see? Yes, absolute mirror images. Yes, great then. Okay, now you come to MAA3 type, COEN3. What are you getting? What are you getting? See, very easy. Again, D form and L form. These are just examples. I think if you just go through the slides, and once I provide it in the Telegram channel, you will be able to get it. This is food. Okay. All right. Then you again have this cis type of COEN2, Cl2. Again, you are getting the mirror images. So these are just examples. You can just go through. Okay. You can just go through them and you will be able to understand. Now I have a question for you. Okay. The complex PT, PY, NH3, Br, Cl will have how many geometrical isomers? I actually told you this. Let's take a look at it. What is this kind? This is M, okay, A, B, C, D. How many geometrical isomers are possible? Are you sure, Singham? Okay, Harini, okay. Don't worry, since we have already come to an end now. Let's do one thing. Let's just wait for the elaborate one, okay? Alright. I think by November, I'm anyway going to complete your syllabus at least once. After that, from December, we will again start with elaborate teaching. Does that make sense? And every chapter will have at least 4 to 5 sessions. Alright, Harini? Okay? Chalo. Very good, very good. How many of you have given me the correct answer? I can see that. Tilagavati, very good. Some of the students are saying 4. How 4, bacha? How is it 4? How did you get 4? Hey, the answer is 3. Huh? I showed you this. You forgot. There is 2 cis and there will be 1 trans. No. See? Either pyridine will be at the top or it will be at the bottom, or it will be like this. There are only 3 possible, bacha. Only 3 possible. Okay. Alright. So that's it, everyone. This is where we come to the end of coordination compounds. But yes, this was only one shot divided into 2 parts. Otherwise, this is a huge chapter. If I would have taught you everything in one go, I think everything would have been on top of your head. So I think this is how we should have taken it. Yes, 2 cis, 1 trans. That's what I told you, right? So we are done with coordination compounds. I will be recording one video of P block. Please go through this during the vacation. Once I come back, I'll take a test on it, okay? I will be taking a test on it, and any which way, even during the holidays, I'm available on my Instagram if you want to follow me, and if you have any doubt that you want to ask me, please go ahead and talk to me here, okay? Alright. Applications. Achha, that we will do later. Don't worry. That I think I can make a small YT short and I can tell you, okay? Singham, I'll make a small YT short and I'll tell you what are the applications of coordination compound. Don't worry. So thank you so much. That was all for today. I hope that you all enjoyed the session and I hope that you all understood it. If you did understand, then please don't forget to share it with your friends. Let them also know, because it's what? Exam oriented channel and exam oriented session. So the more people get benefited from this, the better. Alright. With this note, everybody, tara bye bye, and we are going to celebrate our vacation. You should too, but do study a little bit, okay? Every day at least 2 to 3 hours you study. After that, everything is fine. Then you can have fun. Alright. Chalo. See you all. Have a nice holiday and happy Diwali in advance. Bye.